using quaternions to prove theorems in spherical geometry by Marshall and Whittlesey from Cal State University, San Marcos. Marshall?
All right, thank you. So, to show how to use quaternions in spherical geometry, it all involves the usage of essentially quaternions to do operations in R3. And to see how that kind of thing is done, it helps to look back at what complex numbers do in R2. All right, so as is well known, if you have a complex number A, and you multiply it by the complex number e to the I theta cosine theta equals I sine theta, then that causes the complex number A to be rotated by the angle theta counterclockwise. All right, so B is A times e to the I theta, and if you divide by A, then you can write that as BA inverse equals e to the I theta. Okay, and there's nothing special about the placement of A and B. They are of the same norm, but if I had, you know, this whole situation rotated a little bit around like that, and A were here and B were there, then still BA inverse would be e to the I theta. Okay, so I'd like to see in a few minutes how this can be generalized to 3 dimensions using quaternions. All right, so this slide, I basically have a number of sort of things that I think are familiar to anybody who knows anything about quaternions, but just in case some people aren't, the quaternion algebra is a set of objects of the form A plus BI plus CJ plus DK, where I, J, and K are all square roots of -1, and you multiply them in certain ways. IJ is K, JK is I, etc. And you can multiply these quadruples together and get other quaternions. If you have a quaternion A plus BI plus CJ plus DK, its conjugate is what you get when you negate all the terms involving I, J, and K. All right, and the construction of that does the same thing as it does with complex numbers. It gives you an avenue to the so-called inverse. Okay, Q inverse is the conjugate divided by the square of the norm, just as it is for complex numbers. Now, the main point of this page is to take a look at first what happens when you multiply pure quaternions, all right, things that don't have a real part to them. Okay, so forget about the A bar. What if you just have something of this form, just a vector in R3, okay? So that can be regarded a vector as a kind of quaternion, and often called a pure quaternion. All right, so take 2 vectors in R3, x1, y1, z1, x2, y2, z2, and multiply them together using the quaternion product. Okay, now if you remember nothing at all from this talk, remember this. Okay, this is, to me, the thing that makes quaternions very interesting relative to 3-dimensional geometry. Okay, if you multiply some of those 3 and the sum of those 3, you get 9 terms. Okay, some of them are real. Okay, so the terms involving I, J, and K are all real because they involve I squared, J squared, and K squared. And that becomes minus this, minus that, minus that. And the terms that are not real, all right, involving, for example, the JK terms, when you take this J times that K, and that K times that J, KJ multiples involve I, and that produces this term. The KI terms, IK and KI, produce the second term, and then the IJ and JI terms produce the last term involving K, since IJ is K. Okay, and if you look at this, you got the sum of those reals plus the sum of those non-real terms. What do we have? All right, well, as everybody knows from 3-dimensional vector geometry, that's the negative of the dot product with the 2 vectors you started with, and this set of 3 is the cross product. Okay, so this to me is the thing that connects the quaternions, the quaternion product with the vector products that we're used to. Okay, the quaternion product of 2 pure quaternions is minus the dot product plus the cross product. And to me, this is kind of the answer to any student in vector calculus who might ask, you know, why are there 2 products for vectors? Well, there aren't. Okay, there's one. It's the quaternion product, which connects them. Okay, it's just that the dot and the cross product are kind of the components to them. Okay, and so any historical discussion, I guess, about, whether the quaternions are good for something and whether the quaternion product helps us do things kind of comes down to the idea, well, do you want to talk about the dot and the cross product separately, or do you want to talk about them together? Components or together? All right, so that's a helpful thing even in a vector calculus class. Some interesting properties about what happens when we multiply quaternions. So any quaternion, there's a real part, the first term, and the adjacent part opposed to the non-real part. And we can view that as a real part and a vector part. The same way with complex numbers, we have a real part and a complex part. Okay? And just as with complex numbers, sometimes it's helpful to break a quaternion up into real and vector parts, and sometimes it isn't. Okay, so I want to break it up into real and vector parts here and kind of see what happens. So if I take P and Q, okay, with real part and vector part times real part times vector part, okay, then we just have something we can FOIL out, and let's see what happens to that. Okay, and particularly I'm going to focus on the real part of a product of two quaternions. Okay, so I have real plus vector, I just FOIL it out, and I have four terms which kind of ran off the page there. But let's see what happens when we take the real part of this. Well, all right, the first two terms is the product of two real numbers. Of course, that's real, so that's just part of the real part. The second two terms are a real number times a vector and a real number times a vector. Those are pure quaternions, okay, so I have no real parts. The real part of that and that are both 0. And then the last part, that's the product of a pure quaternion and a pure quaternion, just the product of two vectors. Okay, well, we saw on the previous slide that if you take the real part of the product of two pure quaternions, that's just minus the dot product. Okay, and we get a very useful fact about any pair of quaternions, that if you take the real part of the product of two quaternions, it's the product of the real parts minus the dot product of the vector parts, which is very much like what we get for complex numbers. Real part of the product of two complex numbers is real minus imaginary. Okay, so this is a handy little equation to make use of. All right, another little interesting fact about quaternions that for me falls into the world of facts every math major should know at some point. All right, let's see what happens when we take the product of three of them. Now, it's a little bit more than I have time for in this talk to point out the key fact that quaternion product is associative. Okay, we probably wouldn't be talking about them as much as we do if it weren't. Okay, so let's just take that fact for granted, that if you have PQR, then if you do P and Q first, it's the same thing as if you do Q and R first. Okay, well, let's see what happens when we take the real part of that. Okay, well, so we have a real part of quaternion is the real part of quaternion. Let's use what we had on the previous page. We said the real product of the product of two quaternions is, left side, real minus vector, and that's the same thing on the right side. The real part of the product is real minus vector. All right. Now, specifically, the case I'm looking at here, what happens if P, Q, and R are just pure quaternions? All right, they're just vectors, so no real part. Well, that would mean that the real part of any one of the PQR is 0, which makes that term vanish, and it makes that term vanish. All right, so if these are all just vectors, then I'm just left with the vector part of the product of P and Q, viewed as quaternions. Dotted with that one is the dot product on the other side. Then, of course, the minus signs drop out, and the vector part of this quaternion, again, P, Q, and R are pure quaternions, so the vector part of R is just R. And then, using the helpful fact that we noted, when you look at the product of two pure quaternions, just vectors, then their vector part must be the cross product. And that's, again, true on this side, the left, and on the right. So I get a P cross Q there and a Q cross R there. So, what's the point of the slide? Well, if you take the associativity of the quaternions and just take their real part, the consequence is this classic vector triple product. Okay, so for me, that connection is indispensable. It's something that every mathematician should know. Okay, it brings the quaternions to life. Okay, and you can similarly, I don't have time today, but you can similarly get the identities involving the triple vector products. Okay, so now what about spherical geometry then? Well, to generalize what I had regarding complex numbers a few minutes ago, now let's suppose that A and B are vectors in R3. Okay, again, we're thinking of them as quaternions. Then a key result about this is that, just as I had before with complex numbers, if A and B, they're of course lying in a plane, we'll assume they're non-zero, so that they lie in a plane, they have an angle theta between them. Then, if you look at this quantity BA inverse, okay, it's not quite the e to the I theta that it was for complex numbers, but it's something very similar. BA inverse, where we view B and A as quaternions, and this is the quaternion division, if you will. It's cosine theta plus sine theta E, where theta is the angle between them, and E is the unit vector, which essentially is the one you get from the cross product of A and B. Okay, it's the one that makes A, B, and E a right-handed triple. Okay, so a quick proof of why this is so. All right, so this picture down there is the same as the bigger one on the previous page. Okay, I'm just going to quickly illustrate this for the case that A and B. So A and B were assumed to have the same norm. Let's just, for convenience, assume they're both in norm 1. All right. All right, then A inverse is its conjugate divided by its norm. But A is a norm, well, it's norm 1, first of all, and it's also a pure quaternion. So its conjugate is just as negative, a handy fact here. So the A inverse and B inverse are both just their negatives. So with that being the case, what is this cosine theta plus E sine theta thing? Well, cosine theta, as everybody knows, that's found from the dot product of two vectors, and we get the sine from the cross product. Again, A and B both have norm 1 here, so I can actually say this actually equals directly the dot product plus the cross product, where E is, of course, the direction of the cross product that we get from the right-hand rule. Okay, and so then we just have to fiddle around a little bit with signs. A dot B is B cross A, and then B dot A is minus B dot minus A, double minuses gives us plus. The cross product is anti-commutative, so A cross B is minus B cross A, and then put that minus in there with the A, convert the minus A to A inverse, and what we get from all of this fiddling is that minus B dot that thing plus B cross that thing. And of course, as we saw a few pages back, that's just a quaternion product of the two vectors BA inverse. Okay, so BA inverse is just that quaternion cosine theta plus B sine theta. All right, so this connects quaternion divisions somehow with angles and rotations a little bit in 3 dimensions. All right, and what's more, let me just emphasize in the previous page here, once again, it did not matter where A and B were in the plane, as long as they were in the plane perpendicular to E. Okay, so if I rotate A and B around this circle that I've drawn here in space, okay, as long as the angle between them is theta, then BA inverse is cos theta plus E sine theta. So if A were there and B were over there, and the angle between them, then BA inverse is cos theta plus E sine theta. And what this says is that it associates somehow, if I can take this arc between A and B and move it around this circle, as long as I maintain its orientation, it associates with every directed great circle arc. Okay, if we have a big sphere here containing this circle and of course E, and the arc from A to B is a great circle, then it associates to that directed great circle arc a particular quaternion. And what's more, all right, so this picture illustrates this somewhat better. If this were the directed great circle arc on a particular hemisphere, but there's a big sphere underneath it, then this particular directed great circle arc has a quaternion associated with it that I find by taking that divided by that. All right, and it doesn't matter if that red arc gets rotated around the great circle that it sits on to be, for example, this one from A to B, BA inverse is the same quaternion as that times that inverse. Okay? And this gives us a sense of spherical vectors, okay, in that somehow this red arc indicating in a way, a rotation in a particular direction of a certain magnitude, theta, all right, this red vector, if you rotate it around, it's somehow associated with the same quaternion, in the same way that if you have a vector in space and you parallelly displace it, it's the same vector. Okay? And that principle, that geometric principle, gives us a way to illustrate the idea, how would we take this as a spherical vector and say this green one at the back is another spherical vector and another great circle, how would we add them together? Okay, well, we add vectors head to tail, and if you have two vectors in space, how do we add them head to tail? Well, you have to move them so that the head of one coincides with the tail of the other, and then you add them head of one to the tail of the other. Well, that's what we do here as well, okay? What you do is you just rotate the red one around so that its head coincides with the tail of the green one, which is rotated around in the great circle down here. Okay? Red one points to here, green one begins there and goes over here, and the sum of taking that one and that one gives us this purple vector pointing from A to C. Now, what's really great about that is not just the fact that you can draw this picture and you get the geometry of adding heads to tails, but it matches up with the Quaternion algebra. Okay, the fact is this red vector, that's BA inverse, the quaternion associated with this BA inverse, quaternion B, and the quaternion associated with going from B to C is CB inverse, that's W, and the product of those, because the Quaternion algebra is associative, has B inverse B canceling out to give us CA inverse. And so the quaternion associated with that times the quaternion associated with that in the right order gives us the quaternion associated with that. So if we regard the arrows as somehow spherical vectors, the quaternions capture the geometry of adding those together. And what I'd like you to do, and I'm not sure exactly how much time I have left at the moment, but 7 minutes. Okay, good. To illustrate now how that kind of principle allows you to prove, in particular, theorems about spherical triangles. So that's what I have up here. This is a triangle with great circle arcs. So there's a sphere, and each one of these points, A, B, and C, is a point in the sphere, and AB, AC, and BC are the great circles between them. And I've drawn each of these sides as directed great circle arcs, from A to B, from B to C, and from A to C. All right? And spherical geometry, at least a lot of spherical trigonometry, is about coming up with relationships between, number one, of course, the sides of the spherical triangle. The sides are measured via the arc measures of the sides rather than the length. It's the measure of the central angle of the sphere for each side. And of course, the angle is the angle between the great circles as they meet at the vertices. Okay? So, as I indicated on the previous slide, if you go from A to B and think of that as being some sort of spherical vector, the quaternion associated with that is BA inverse. B to C has a quaternion associated with that with CB inverse. And A to C has a quaternion associated of CA inverse. And the product of this one times that one is that one. And what we want to do is write each of the BA inverse, CB inverse, and CA inverse in the form cosine something plus sine something times an E. Okay, so for each one of these sides, all right, there is a perpendicular vector E. So if I have a vector to A and a vector to B, then E is essentially the direction of the cross product. That's up here. All right, so EC up there is the perpendicular to this side. This side has a perpendicular which points out that way. And this side here is a perpendicular which points out this way. Okay, so each great circle arc has a perpendicular. And this one here is cosine that plus the measure, I'm sorry, if this side has measure gamma, then this quaternion is cosine gamma plus sine theta gamma times the vector. This side here is measure alpha, so its quaternion is cosine alpha plus sine alpha times the perpendicular E. And the third side is cosine beta plus sine theta times that vector. And the product of those two gives you that, right? So that's this thing times that. That's the gamma 1 times the alpha 1 gives you the beta 1. I have it on the next page. All right, product of that quaternion times that one is the third one. Okay, so it's a statement about quaternions, which is just teeming with constants in the spherical triangle. Okay, we have the one for one side there, and another side there. All right, and to squeeze out that information, well, we just multiply out the left side. The right side is what it is, and you have all sorts of coordinates of quaternions, which can be set to be equal to each other. Okay, and here I'll just take a look at what happens when you equate the real parts. All right, so there you have to FOIL out the top to get real parts. The cosine alpha, cosine gamma, obviously that's real, so it's a real part of itself. The cross terms involving EC and EA, those are pure vectors, pure quaternions, so vectors, so their real part is 0. And then the last term, sine theta, sine gamma times the product of EA and EC. Well, EA and EC are just vectors, so their product, quaternion product, is just minus the dot product. And then on the right side, the real part, which is cosine theta, that's a vector, so its real part is 0. Okay? And then the last thing we need to do is use a property that's a big one in spherical geometry, that if you look at these two vectors, EA and EC, so I forgot what they are, we can go back to the previous page. The EA and the EC. EA is what we call a pole of this side over here. So B and C are points in the sphere. There's a plane at the center of the sphere containing them, and EA is the pole of that great circle. If you consider this an equator, then this is its pole. And the same thing, this point here in the sphere is a pole of that side, and that's a pole of this side. All right? And it's a key property that's not difficult to prove just with a little bit of geometry, that the angle between two of these poles, all right, is the supplement of this angle right here. Okay, and so when I take the dot product in the next page of a couple of those poles, all right, the EA dot the EC, that turns out to be EA dot EC. It's just the cosine of the supplement of the angle at B. Okay, so using that, then what falls out is just known as the spherical law of cosines. Okay, it's a statement involving the sides, measures the alpha, the gamma, and the beta of the lengths of the sides of the spherical triangle, two sides, and an angle between allows you to get the third side. Okay, and again, I don't do it here, but if you fiddle around with essentially squeezing out more components, you get more formulas relating sides and angles in the spherical triangle. All right. So that's, I think, about where I'll stop. A lot of these ideas, and it goes on much further than this, than what I can do it in a short talk like this, but I have an upcoming book with CRC Press called Spherical Geometry and Its Applications, where I have a chapter which features how to use quaternions to prove a lot of interesting things. So if you're interested in my book, I would be glad to know who you are. I'll just circulate a little piece of paper, you give me name and contact info, and I'll let you know when it comes out. So I'll stop here. Thanks.
Quick question. You have a minute or so for a question. So mine's just completely off the wall. What led you in this direction to sort of see that this is spherical trigonometry could be randomly captured by things related to quaternions?
Well, I mean, naturally, people often, after vectors and quaternions sort of emerged from the 19th century, people figured out how to do lots of things in 3 dimensions with vectors. And so I believe Hamilton originally in his work, talked about how to do things in spherical geometry with Quaternions. I actually myself have only one reference, a vector analysis book by Louis Brand, which goes into some detail about how to do Quaternions, and I just frankly just found that fascinating, and just the fact that it doesn't seem to be very well known how to do this in an elegant way. So if anybody, this is Louis Brand, vector analysis, I forgot the full title, 1947. If anybody knows of any other references which gets into this kind of thing, I would appreciate knowing about it.
Thank you.